Good afternoon, students. Once again, uh, we are going to look at lesson number 11, that is input output organization today. So, the first thing in this that I'll be discussing is about the input output interface. Now, what is an input output interface? An electrical component that comes in between the processor and a peripheral device. Okay, what is a peripheral device? An IO device is also known as a peripheral device. So, an electrical or electromagnetic component that serves as an intermediary between the CPU and the IO device is known as a IO interface. Okay, it interfaces both these units, that is the processor on one hand and a peripheral device. It may be a printer, it may be a keyboard, it may be a pen drive or some other kind of magnetic tape or magnetic disk, etc. Any IO device, right? Now, what is the job of an IO interface? You see that we have a IO interface placed in front of each of the IO devices. Again, somebody wants to join. Okay. Now, you see that these IO interfaces, each device has its own IO interface. Okay. Now, what is the job of these interfaces? Well, the primary job of any IO interface, and I told this to you earlier in one of my earlier lectures as well, that one of the primary jobs of a IO interface is to act as a buffer. Okay. Now, when it acts as a buffer, what it does is that it reduces the gap between the speed of CPU and an IO device. All of us know that processor is generally very fast. It works in the speeds of nanoseconds, but the IO devices especially may be very, very, very slow. Also, because they are dependent upon the user. This means that firstly, the IO devices may not be designed to be as fast as a processor. They may not be designed to match the exact speed of a processor. And secondly, because of the user who is operating that particular device, there may be a much further delay in giving the input or receiving the output. For instance, we have already taken this example and I'm reproducing it once again for your benefit, that it takes us almost, a fraction of a second to blink our eye, right? And in that time, the processor is able to complete at least, 10 raised to the power of 6 or even more, tasks, right? So even when we have just blinked our eyes, that is the speed of a processor. Now let us compare the speed with the speed of a keyboard. Okay. So a keyboard obviously itself is extremely slow when we compare its data transfer rate to the data transfer rate of the processor. But also because of a user, let's say if I am sitting here and I just pressed a key, let's say I gave a character A, and then before I type the next character, I would like to take a sip of my tea. Or I may just like to, chat around a bit, right? And then I press the next key. So the idea is similarly with the printer, please see, once the printer gets stuck or there is no page, a user may take 2 or more minutes to even, feed in new pages, right? So there is a considerable amount of difference between the speeds of these two units, that is the processor and the IO devices. As a result, the interface typically has a buffer, also sometimes called as the data register. You can see this is the this is the blow up of uh, these interfaces. So what does each interface of this kind look like? You can see here. So each such register has something known as a buffer or a data register, which stores the data, excess data. So suppose the processor has given 16 bits of data, or it is sending the data at its own rate. One word of data the processor has passed to the interface. So before passing it on to the IO device, the data goes into the from the CPU, it goes into the data register of this interface, where it is stored till the IO device becomes capable of holding the data, of accepting the data. Okay, so once it is available, once the IO device is available, then that data will be transferred to the IO device at the speed of the IO device. Okay, now when this gets empty, then if you remember, we set up a flag. We use the flags FGI and FGO, right? So it sets up a flag to indicate that I am now ready for taking more data from you. It indicates, the interface indicates to the CPU. Now, how does this indicate? So you see this flag bit here. There is another register called as the status register in the interface. This status register consists of various bits. So you have also implemented a status register in your CPU sim machine now, right? Each bit of that status register can be used to indicate a different control condition. For example, we have used the 0th bit in your CPU sim register to indicate the halt condition, right? That means when we set that bit to 1, we indicate to the computer that we want the machine halted, right? Machine means the assembly language program that we're writing, right? So similarly, the status register out here contains many bits, okay? Some bits out of which are flag bits. These flag bits are nothing but FGI, FGO kind of bits, which indicate to the CPU when the IO device is ready for transfer. Okay, now when the IO device has to transfer the data to CPU, it is very slow, right? So it will transfer its data on the IO bus. It will transfer the data into, it will first go to the interface rather than going directly to the CPU. That means instead of going directly to the AC or the input register, it first goes to the data register of the interface. The interface, now suppose, for example, we know that one character is equal to 8 bits, right? And suppose the data transmission rate between the interface and the IO device is only one character at a time. Then, and the word length is 16 bits. So the CPU word length is 16 bits. So one character will first be transmitted from the IO device to the interface. It will be stored here in the data register. Then another character can be transferred here. Okay. And when this becomes full, that means all 16 bits, that is one word length, is completed. Then that data, then the appropriate flag bit can be set to tell the CPU that, the input is now available. FGI can be set to tell the CPU that input is now available. Please accept it in the in one of your registers. Okay, for example, the input register or the accumulator, right? So this is how the interface works. So the first thing that we saw was that why do we need a IO interface? We need a IO interface to reduce the difference in data transfer rates of the peripherals and the CPU. The second important thing that I told you is that the word length of CPU may be different from the data length of the data format which is supported by the IO device. For example, we are transferring only one character at a time, that is 8 bits at a time here. And if the word length is 16 or 32 or 64, whatever, then that word length may be transferred between the interface and the CPU, right? So the word lengths of the CPU and the memory and the IO device may all be different. Okay, so that is what the interface understands. That is what the interface understands. It keeps on buffering the data to act as an intermediary between the processor and the IO device, right? Then another thing is that we see that even different peripherals, you see these peripherals, so different IO devices have a different manner of operation. For example, please see, even when I talk about a mouse, then a mouse with a rolling ball will operate differently from the mouse with that operates with a LCD, the light, right? Similarly, there are different types of printers. There is a laser printer, there is an inkjet printer, yeah, right? There is a normal, very old, sophisticated printers are also there, right? Dot matrix printers they were called, right? So the manner of operation of all these IO devices are very different from each other. Okay, so who understands how a particular device works? It is this interface that understands how exactly this particular device works. Okay, and it acts as an intermediary between this device and the entire computer system for this device. Okay, so if you just try and recollect, whenever you get a new IO device for your computer system, what happens is that whenever you plug in that device, first of all, a software of that gets installed in your system, right? What is that software? That is actually a part of this interface. That is actually a part of this interface. Why do we need to install the software whenever you install? What do we mean when we say that we are installing a printer on a system? This is exactly what we are saying, that we are actually trying to install a software that understands how that particular printer will work. Okay, what are the modalities of that printer, and is also capable of dealing with the windows or the processor or the operating system on our system. Okay, so that software is a part of these interfaces, that they are a part of these interfaces. Is this clear to everybody? Is this
Yes.
clear, right? So these are the benefits of using a IO interface. Now the next thing that I want to introduce to you is what is a IO bus. A IO bus is typically a set of lines, that means wires, that carry the data, the address of the IO device with which the input output is to be performed, and the control commands. Control commands such as, uh, the very simple ones are read or write. And there are actually four kind of control commands. I will be going over them very soon. But uh, overall, what is a IO bus? An IO bus is a set of lines, that is a set of wires, which can be further divided into data lines, address lines, and control lines. These three lines, that is wires taken together, make up a IO bus. Please see, any bus for that matter, whenever I talk about any bus, will always consist of these three lines. That means obviously any bus, let's say I'm talking about a memory bus, then what do we mean by a memory bus? Memory bus means a set of wires which connects the memory to other parts of the computer system, right? So again, even that bus will require to have data lines because we need to send data, and the address, right? So where in the memory you want to write down something, right? And the control, for example, where what we want to read from the memory or we want to write from the memory. So all these lines are required. These are a part of any bus that we talk about in general. Okay, so but here what we are looking at right now, what you are looking at is called a IO bus because this is dedicated, these lines are dedicated, let's say, for the input output purpose only. Okay, now let us look at the four types of control commands that I mentioned. We see these are very, very important, even from the point of view of your exams. So what are control commands? There are four basic kinds of control commands. Okay, there are four basic kinds of IO commands. Okay, also known as the control commands. The first one are control commands themselves. The second type of control commands or IO commands are called the status commands. Then the data input and data output and the data input commands. Now, what do we mean by control commands? Control commands are those commands which are issued, let's say, by the processor to a particular IO device to do a certain job. For example, it may tell the printer to, display the message that the please feed, tell the printer to go on to the next page. So whenever your file printing is completed, right? Suppose it had 2.5 pages. So after printing the last page, the half page, the printer automatically shifts the entire page up. And if you've given a new file, it will start printing it from the new page, right? So going over to the next page, for example, in a printer, or uh, rewinding a particular tape or going forward two sectors on a magnetic tape. Okay, so the or you know rewinding the back spacing the tape by a certain number of records. So all these are some jobs to be done by the IO devices, okay, to prepare them for the IO, for the input output, right? So these are known as control commands. Then the next set of commands is the status commands. So status commands are typically used only to check the readiness of a IO device for doing IO. Okay. For example, checking whether the printer is ready. So looking at its ink levels or checking to see if there is a jam in a printer, or checking to see if the mouse pad is working or not, it is enabled or not, whether a particular sector on a on your magnetic disk, for example a pen drive or something that you just inserted in the system, is readable or not, right? So sometimes it gives you a error that there are bad sectors, right? So these kind of commands are known as status commands. The next are the data output commands. So what happens during the data output? As I just told you, the data is transferred from the IO bus to the interface register first. Okay, so the data is transferred from the IO bus to the interface register, and in the next step, the data is transferred from the interface register to the keyboard. Data output means processor is saying, I want to give you the output. So the data is taken from the processor. The processor has kept that data on the data lines. So the interface register will match its address. What does the processor do? The processor puts the data and the address of whichever IO device it wants to communicate with. The address of the corresponding register it will put on the address lines. Right, the data is put here, the address is put here, and the data output command is put here on the control line. Now all interfaces receive these commands, but as soon as all interfaces receive the output command, they will check first to see if their address matches with the address placed on the address lines. If the address matches, then they accept the data from the data lines and temporarily store them in their own data register and later pass them on to the IO device. Okay, when it is available. Okay, this is how the data output is done. For data input, uh, the interface will place the data on the data line. Okay, take the data from the firstly, it will take the data from the IO device and buffer it so as to match the word length of the processor. Then when the word length is when the data register is full, when its data register is full, then it places the data onto the data line. The address of the memory word or the register to which the data is to be communicated, it puts here, and the uh, um, request for data input will be put on the control line. Okay, so when the processor sees this input request, it will uh, get interrupted. If you remember, we talked about this. So it will get interrupted, pause whatever instruction it was about to execute, take the input, and then go back to doing its own job. Okay, back. So these are the data output and the data input commands, right? Now, in your exams, for example, they may just ask you what are the different types of IO commands, give examples of each, or they may, give you things like, what is identify the type of IO command. So, uh, checking for cartridges or backspace the tape by one record. What is the type of IO command involved in these? Okay, so that is how one marker generally, questions are asked. Now, uh, see this, as I told you, this bus is the IO bus. Similarly, there is a bus generally which does the memory transfers, which is also known as the memory bus. Okay, now the question is that whether we should be having a single bus for both memory and IO or two separate buses. The first option in this case is that we have two separate buses. That is, there is a completely different bus. That means different data lines, different address lines, different control lines that go from the processor to the memory, and different data lines, control lines, address lines that go from the processor to the input devices. Okay. Now, the second option in this regard is that we keep the same data lines and the address lines, okay, but we use two separate control lines. Okay. Now, what happens in this case is that there is a separate address space for the memory and there is a separate address space for IO. Now, what do I mean by this? Uh, See, the IO devices also need space to store their data. you've seen that there are various registers of each interface, etc. Right? So this data needs to be stored somewhere on our system for each IO device. Right? Each interface will have its own set of registers. So only two are shown here. There may be uh, a few more, right? Very few, वैसे, but then there may be a few more, right? So we need space for uh, storing these registers. And then we know that there is a main memory, right? RAM, as we know it, right? So the first option, uh, you know, had it that obviously the memory address space, that means where the memory data is stored, and the IO address space, that means where the IO data is stored, are totally different, right? Now here also in option 2, we have the address spaces for memory and IO separate. We have two separate spaces. Now when I say, when the CPU, for example, puts the data on the data lines. Now in this option, we are trying to share the data line as well as the address line. So when the CPU puts the data on the data line and it puts the address, let's say 1 or 100, okay, on the address lines, then it may happen that there may be a address 100 in this address space, that means in the memory RAM, and there may also be a address 100 if there is a separate space for IO. Okay, this will also be some kind of a memory only, specially reserved for the IO devices, right? So there may be some address 100 here also, right? So how to distinguish whether this data, which is meant for a particular address 100, is actually meant for the memory or for IO? For that, we have separate control lines. We have separate control lines. So separate control lines means we have two wires, one which is dedicated just to indicate whether it is a memory read or a memory write, and similarly a pair of wires which is completely dedicated to indicate whether it is a IO read or a IO write. So suppose the processor has placed the data here and the address 100 here, and it activates IO read, then it means that the data is to be read from the 100th location from the IO address space. If it uh, activates memory read, then the data is to be read from memory address 800. Similarly, memory write means to be written to memory address 100. IO write means to be written to IO address 100. Okay, so this is the second option. In both these cases, the first case as well as the second case, these are the cases of isolated IO. Isolated IO means where the uh, input output address space is separate from the address space for the main memory. Okay. Now let us look at the third option, which is also known as the memory mapped IO. In the memory mapped IO, please look at the name again very carefully. As the name suggests, the IO and the memory are address spaces are mapped. That means physically the processor, the system in the computer system, there is a single storage area which is given to both the main memory, and in which interface uh, registers are also stored. Okay, so each IO device's interface registers are also stored in the same address space and the main memory is also located somewhere in the same storage area where the IO is placed, right? So this kind of a scenario is known as the memory mapped IO. Now what happens here is that we have not only common data lines and common address lines this time, but we can also have common control lines this time. Okay, now how is that? This is because now when I place data on the data lines and address on the address lines, then suppose the address is 100, then the address 100 can obviously only belong to either the IO interface registers or the memory word, right? It can only be in the bag of main memory or the IO interface registers, right? So we don't have to distinguish with the help of control lines that whether this particular data transfer is intended for IO or for main memory. We can simply, the processor simply puts the data here, puts the address here, and gives a common command read or write, and whatever address, that address belongs to whoever of these two contenders, responds, and the uh, data transfer is done in a similar way to both the memory and the IO. In fact, even the same commands which are generally used for the memory, okay, data, read and write, what commands are we using? We are using the commands that we've seen in chapter number 5. We've seen separate commands for input output and the memory read write. Yes, so we can use the same commands for memory as well as for the IO, because the processor will then not have to distinguish whether it is sending the data to IO or to main memory. It is just sending it to a storage area, out of which some addresses have been given to the IO devices, the other addresses have been given to the memory, right? So this is the third option, which is also called the memory mapped IO. What are the differences between the memory mapped and the isolated IO? Let's just do a quick revision once again. So there is the address space for IO in the memory is same in the memory mapped IO, whereas here it is different. Then same control lines. The control lines are different here. The same instructions can be used in the memory mapped IO as I just told you, and therefore generally even you've seen in chapter number 5 that for input output you've seen a very small number of instructions. Same is the case in generally most of the computer architectures, that for IO the number of commands are limited, whereas for memory there are a lot of commands, maybe even sophisticated commands. So in this case, memory mapped IO, the same commands, since the same commands are being used, so the repertoire of the IO commands also increases. That means a large number of sophisticated commands can also be used to do IO transfer. But here, there are a small number of instructions which are available for the IO. Now, there is a disadvantage of the memory mapped IO, however, obviously, that since the main memory, that is the RAM, has to share its address space with the IO devices, it limits the range of the main memory. Obviously, we can store lesser data, lesser address space, lesser storage is given to the main memory, RAM, and therefore the amount of data that can be stored in the RAM is therefore limited. Okay. So these are the differences between the memory mapped and isolated IO. Okay. So, I would like to stop here today, but I want to give you an overview of the mm, timeline. So we will just need two more, only two more lectures are now required to complete the course of CSA. So I'll take those two lectures next week, and we will be finishing with our course. I have at no point, tried to do things at a very fast pace, or without pausing for you to understand. So I hope that you people are able to replay my lectures and understand all the topics once again once you replay the lectures. um, that is why I have taken special care to go slow, since you are first semester right now. So I have typically tried to go slow, very slow, pausing for you at each step, explaining the things again and again. Okay, so I hope, students, that you have found this useful. Have you?
Yes, ma'am.
Yes, ma'am. Thank you so much,
Yes, ma'am.
ma'am.
You're most welcome, Beta. You're most welcome. It's been an absolute pleasure teaching all of you. And I hope you have enjoyed the subject. Have you?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Yes,
See,
ma'am.
see, I'll tell you one of the things about teaching a particular subject or introducing a particular subject is, you can obviously, there are, when we are talking about computer system architecture, for example, so there are many new architectures which are available today in the market, and they will keep on coming, right? So the idea is not to give you a comprehensive knowledge, okay, but to set your basics right. Once you get interested in a particular subject, you know then it is very easy and very likable to add in more knowledge. It becomes interesting to add on more knowledge, right? So it is with this intent that I have taught you, that you will, whenever you look at the subject, you will look at it with a lot of liking and interest, so that you can continue to grow your knowledge bases more and more. Okay, this is a subject which is covered in substantial detail in most of your entrance exams as well. Okay, these are the very basics of a computer system, which are very essential to understand. Okay, okay. Now, so I'll take two lectures more now, and I think we should be able to, wind up our remaining topics. But before we go, uh, I'd like to discuss about your CPU sim practical. So you will be having your practical. I sent the message through your class representative. You will be having your CSA practical on 4th March, 9:30 a.m. most probably, but I'll let you know the time once again after rectifying it. See, what are you required to do? So, I will be sending you a program. Okay, I will be sending you some questions that you will be required to execute on your end, and uh, then you will be required to send me back your CPU file and your assembly language program, that is the .a and the .cpu file, that means the entire machine, back. Okay, you will be able to you will be required to mail me back those two files. Okay, so whatever number of assembly language programs you make and your entire machine, you will send me. I will assess them and then I will allocate your marks. Okay, just give me 2 minutes. Let me complete. Let me just brief everybody what I'm saying. No, Kirti, please stay on. This is very important. Please wait for 2 minutes. Please wait for 2 minutes. Then I'll ask you. Okay. I'll ask everybody, Disha. Okay. Wait for 2 minutes. Let me just complete. Let me just give you a general outline of what will be asked to you in the practical. So typically, please see, you will be asked to make a machine first of all. Now, what do you mean by this is that I will tell you that these registers are required, and this is the specification of RAM that is required. So you will have to, the first step will be in your practical, the first step will be to create those registers and create the main memory. Is that clear to everybody? So
Yes,
Yes,
your
ma'am.
ma'am.
yeah. So your machine will be created. Number one. Okay, no problems here, right? The second step is that you will be required to implement the fetch routine. Okay, that is generally the second question. That has to be the second question. Okay, I hope nobody has a problem in that, right? We did that a long way back, right? Then the third question will be to implement 2 or 3 micro instructions, such as somebody may get CLA, somebody may get AND, okay, somebody may get OR, somebody may get CLE or SPA, okay, things like this, right? So you just perform that, then you save your files. Okay, you save your machine, you save your file, okay, the file in which you have written your CLA instruction, the assembly language program, and you send them both. The fourth step will be to send them back on, I will give you a dedicated mail ID. Okay, so you will have to send them back to that particular mail ID with a particular subject. The mail that you send me will have a particular subject that will mention your roll number, okay, and the uh, set. So I will make separate sets so that you get separate instructions. So set A, set B, for example, I may make 2 sets. So whether you are attempting the questions of set A or set B, so you will say your roll number, your name, and then set A or set B. Okay, and you will send me your files. Okay, so this is what you have to do. I'm just repeating. So there is nothing to get worried about here. Everything that I have shown you in the class, they are very simple instructions. For example, CLA, CLE, okay. No instruction is difficult. What you have to do is, first of all, you will have to create a machine. That means create your registers and main memory. Second, you will have to create your fetch routine. Third, there will be 2 or 3 instructions which will be to be executed. And fourth, you will have to save everything and you will have to send those files to me on the mail ID. Okay, so this is how your practical will go. Okay.